Cantilever beams are one of the most important topics at the intersection of biomechanics, instrumentation engineering and biomedical engineering. Cantilever beams are used to model from structures like cilia that line the inner surface of the lungs to make sensors like micro-cantilever beams. In this video, we are going to discuss theory and applications of cantilever beams using small deformations. The way we are going to do that is by discussing an example problem. Following that, we will look at the necessary theory in order to solve the example problem. For the example problem, we are given a silicon nitride beam. Okay, so this has a modulus of 385 gigapascals, Young's modulus. Okay, and it's micro-cantilever, so the dimensions are all in the micro range. The length of the beam is 200 micrometers. If you were to take a particular cross section, okay, and look at it, the height of this beam is 0.6 micrometers. The width of this beam, okay, B, that is equal to 20 micrometers. Such a beam, micro-cantilever beam, is used to detect bacteria. Okay, so antibodies, essentially substances that will stick to certain proteins in the surface of the bacteria, that are all there here at this end. Once you dip it in a medium that has bacteria, bacteria are likely to stick to this, and because of the weight of the bacteria that sticks to this, it's micro-cantilever, and the beam will slightly deflect. Essentially, there will be a force due to the weight of the bacteria. That force will cause the cantilever to deflect. What is given is that a deflection of 10 mm is observed. Here is a correction. This is an example problem from the book. It says it's 10 micrometer, but given that the length of the cantilever itself is like 200 micrometers, okay, I'm going to change the deflection at the end of the beam to be that of 1 micrometers. It's not 10 millimeters, it's 1 micrometers. Okay. Now the question is, how many bacteria did get attached to the tip of this cantilever beam? One more information that's required to solve this problem is the weight of one bacteria, that's equal to 53 nanograms. Additionally, I'm also going to say, okay, so if you had to measure X from the tip of the fixed end of the cantilever beam, okay, the deflection, it's a function of X. That particular function is also given here. Deflection delta is a function of X is given by this. Depends on the amount of force, depends on the X, depends on the length of the beam, E and I. I is the moment of inertia of the cantilever beam. Okay, for a rectangular cross section, I is BH cube by 12. I'm going to write all the powers of 10, the starting of this. So 10 power 0 is 1, I'll start with that, times B. B is 20 microns, okay, 20 micrometers, so minus 6 I have. That times H cube is 0.6 cube, again a micrometers, so it's cube, so it's minus 18, 6 times 3 by 12. This expression, if you pass an estimate, this should turn out to be 0.36 into 10 power minus 24 meter power 4. Okay, so once we have that, this is deflection as a function of X. What we want is the deflection, or what we are given is the deflection at the end of the beam. At the end of the beam, okay, so delta at X is L. When X is L, we get the end of the beam. So deflection at the end of the beam, okay, let's call it delta max or delta at X equal to L. This will be F L square 3L minus L by 6 EI. If you simplify this expression, this will be F L cube by 3 EI. Okay, so I'm going to write this as delta at N. Now what we want is the force, right? If you find out what the force is, the force here is going to be this is in newtons, let's say, it's going to be mass times acceleration due to gravity, where m is the total mass due to all the bacteria that sticks to this. Yep. Okay, so with that, this implies the force that we want to estimate is equal to F is delta n times 3 EI by L cube. Okay, now we can calculate the force that created this particular deflection that's given over here. So let's calculate that. Again, I'm going to write all the powers of 10 at the beginning. So delta n is 1 micrometers. So it's just 1 times E is 385 gigapascals. 385 giga, so it's plus 9. And I, we know, we just calculated, it's 0.36 into 10 power minus 24 divided by L cube. L we know is 200 cube, 10 power 0 minus, it's in micrometers, so 10 power minus 6 cubed is minus 18. So 200 micrometers is over here. If you simplify this, you should get 5.19 times 10 power minus 8 newtons. Okay. So can we find the mass corresponding to that? This is equal to m times g. Okay, the force is m times g. Using this, we can find what the mass of all the bacteria is. Okay, so this implies mass is 5.19 times 10 power minus 8 by acceleration due to gravity, which is 9.8. If you calculate this, this turns out to be 53 approximately into 10 power minus 7 grams. This is in newtons, so this is kilograms meter per second square. So convert that into grams, you will get 53 into 10 power minus 7. So now the problem is straightforward, right? One bacteria is 53 nanograms. How many bacteria would weigh 53 times this? Okay, so number of bacteria is total weight by weight of one bacteria, 53 into 10 power nanograms, so it's minus 9. This is 100. So in this example problem, it differs from the book that I am referring. The book is given as 10 millimeters. I'm going to use 1 micrometers. First thing is, deflection as a function of x is given. We want deflection at the tip, substitute x as L, get this expression. Find the force that would result in this deflection, and we found the force to be this. Once we have the force is nothing but mass times acceleration due to gravity, mg. Now we can find the total mass of bacteria from this, which is 53 into 10 power minus 7 grams. Using this, you could find the number of bacteria using weight of one bacteria. Total mass by weight of mass of one bacteria. That turns out to be 100. But this raises a couple of questions. One, we somehow wrote down this I is BH cube by 12 for the rectangular cross section. Why is that? Second, we also used this particular form of deflection, delta of x is this particular function of x.